This is video number 2 for our review on particle motion. So once again, since you've reviewed the particle motion notes or key facts and watched the other video, you should now try example number 1 and number 2 here on your own and then watch the video to see if you thought through it correctly. So taking a look at number 1, we are looking at a particle motion problem where you're given the position. So many of our problems in the past have been given velocity or acceleration, but this one is about position. So what is the position of the bug when it first starts walking? Well, that's asking for the initial position, so at time equals 0. When we plug 0 in, we end up with 2. There aren't any units here provided in the problem, so we can just say 2. At what time is the bug stopped? If you have a calculator, you want to take a look at the overall graph, but the question is the graph of what? Can we tell from the position graph? Well, if we're looking for the bug being stopped, what we want to look for actually is when velocity is equal to 0. So let's take the derivative. The derivative of position here would be 1/3 times 3t squared minus 7 over 2 times 2 t to the first plus 12. Okay, now the 1/3 and the 3 cancel. The 7 over 2 times 2, the 2's cancel. So we're left with t squared minus 7t plus 12. All right, so now we want to know when does that quadratic, and I'm going to erase the work here because there isn't much space. When is this quadratic equal to 0? We can solve this actually without the graph. We can solve this by factoring. So let's set this equal to 0. We're going to factor x minus 4, x minus 3 equals 0. So the velocity will be equal to 0 when x is 4, or I shouldn't say x, I should say t. When t is 4 and when t is 3. So when is the bug stopped? At least temporarily, it's at time equals 4 and time equals 3. Maybe 4 seconds and 3 seconds. Okay, the next question is, when is the bug walking to the left? In order to answer that, we need to know when is the velocity less than 0. Okay, I'm actually going to take my work up here. When is it less than 0? So we already found the derivative of the position, or found the equation for velocity. It was t squared minus 7t plus 12. And we said factored that that's t minus 4 times t minus 3. Okay, now if you have a calculator you could graph this, but we also know enough about quadratics that we can graph this ourselves. We know that we are going to have an x-intercept at 3 and at 4, and the a value here is positive, so this opens up. So our graph is going to look like this, with x-intercepts at 3 and 4. So when is the velocity negative? It's negative when it's below the x-axis. So it's negative between 3 and 4. So the bug is walking to the left from, let's see, on the interval, parentheses, 3 to 4. So again, this is the interval. It tells you on what interval, or asks on what interval. So we're looking at time, the seconds between 3 and 4. Okay, now there's one more question here, and it's, now imagine the bug's position is given by a new equation. How far does the bug travel on the interval from 0 to 8? Okay, so if we're trying to find total distance here, how far the bug is traveling, we would normally do the integral of the velocity from a to b, dt, and the absolute value. That would give us the distance traveled. But we aren't given velocity, we're given position. For the previous 3 parts to this problem, we could assume that these were non-calculator. This question that I've written in down below in D actually is a calculator problem. And what would also be helpful for this problem is to look at the new notes I gave you on the last page. So here's some new information on finding net distance or total distance. Net distance is given by finding the difference in position or the absolute value in position. If there's no change in direction, then total distance is the same as displacement. So this was displacement. If there is a change in direction, total distance is found by taking the difference in position every time it changes direction. So for example, if we had a graph that went like this, you would find the distance traveled on this section, then the distance traveled on this section, down here, then the distance traveled here, and then finally this last section. And you'd find that distance by finding the difference in position from the start and the end. So let's say the y value here was 5 and the y value here was 10. Well, the change in position is 5. And then you'd find the difference in position from 10 to -5. Well, if you subtract those two things, you get a total distance of 15. And then let's say it went from -5 to, let's say, 8. Okay, so now we have a distance of 13. And let's say this last distance is 3. So we would take all of these distances and add them up for the total distance. So this would be 20, 33, 36. So a total displacement of 36. And we got each of these just by subtracting, like 10 minus 5. Now this method only works if you have a position graph. And position can be represented with S of t or x of t or p of t. But that's how you find it for a position graph. So let's go back to this problem. This is the equation given for position. This is a cubic function, we can tell, because if we multiplied it out, we'd have x to the third. And the leading coefficient is 1, so we know our end behavior is down, up. So I'm going to draw in 2, and mark this as 2, 5, 7, and 8. We know we have x-intercepts at 2, 5, and 7. So our graph is going to look something like this. Right? This is just an approximation. It's going to look something like that. So to find the total distance from, this is going to come down here. I'm going to start at 0. To find the total distance traveled, we're going to need to know the distance on this first chunk from 0 to whatever this highest value is, then the distance on this next chunk where it's decreasing, and then finally the distance on this last part up to where t equals 8. Okay, so how do we find that? Well, the first piece, I'm going to call this the blue piece, it's the absolute value of s of whatever our relative max is here. We can't tell where that max is based on the graph I drew. You'd have to graph this on your calculator, and if you do, you find that the max is at approximately 3.214, 8.209. So we'd find the difference between this point and our initial point. And I'm using s, but really I should be using x, because that's what was given in the problem. Okay, so this first piece is going to be 8.209 minus -70, because x of 0 is 70. So that means that our change in position here is actually approximately 78.209. And that's just the blue piece. That's the distance traveled. Now let's do the green piece. The green piece has its relative min, and again, you'd have to use a calculator to find this exactly. But the relative min here is at 6.119. 0.96. Okay, so this is going to round up to 0.120, comma, negative 4.061. All right, so this next piece is going from x of 6.120, and it's subtracting the value at 3.214. And we already know that this y value is approximately negative 4.061, and our value from before was 8.209. Okay, so when we subtract that and take the absolute value, we get 12.27. Okay, so that's the distance traveled on that next section. And again, we're not talking displacement, but where it ends up in the end, just like how many feet the bug has traveled overall. And then we do something similar for the red section. This is going up until time equals 8. So in this red section, we're doing x of 8 minus x of 6.120. And again, we need a graphing calculator to know where it's stopping up here. And you can either use the table or you can just plug in the value of x equals 8. And this is at 818. So down here, this is going to be the absolute value of 18 minus negative 4.061. So that gives us a distance of 22.061. So now we can add all of these distances together. Sorry, this is all over the place. 78,209, 12.270, and 22.061. And we get 112.540. So this is the total distance traveled in whatever units exist for this problem. All right, so let's clear the page and we're going to take a look at the next overall problem. So in this next problem, we are given a velocity graph. Above, we were given the position equation. So how we answered the problems before is going to look different from how we answer them now. So here it's asking us to find v of 3. Well, since we have the graph of v of t, we can just go to 1, 2, 3. And this is at 1, 2, 3, 4, 5, 6. So v of 3 equals 6. And 11, 4, 5, 6, 7, 8, 9, 10, 11. Looks like it's at about 2. Then it asks for the acceleration at 1, 5, and 3. Now remember, acceleration is just the derivative or slope of velocity. So to find a of 1, I need to look at the slope on this section because 1 falls in there. So it looks like it has a x value of 3 and it's going up 6. So a of 1 would be equal to 2. Then a of 5, want to look for 5. 5 is up here. There's no change in the velocity. Since there's no change in velocity, the slope is 0, and that means the acceleration is 0. And then finally, a of 3. Well, at a of 3, we're actually changing. The velocity is changing. So we can say that the acceleration here it's not possible to determine because on this leading up to or approaching x equals 3 or t equals 3, our acceleration, is 2. So we have a slope of 2 along here. But then the slope up here is 0. And as you approach x equals 3, these two are not going to meet. They're not going to merge. So we're not able to determine the acceleration there. All right, the next question is, at what time does the bug turn around? Well, velocity tells us direction. If the velocity is positive, it's going to the right. If velocity is negative, it's going to the left. So when is it turning around? It's when v of t changes signs. That's when it turns. So let's take a look. That happens at two places, here and here. At t equals 9 and 13. So at t equals 9 and 13, the bug is turning around. Okay, so it's changing from right to left at 9 and from left to right at 13. Okay, let's clear the page again so that we can see these final few problems. All right, D asks, on what interval does the bug have a negative acceleration? Well, again, acceleration is just the slope of velocity. So when is the slope negative? It's negative on this section here. So it's 7 to 9, 10. Let's see. 7 to 10 is the interval. We can say, well, it actually doesn't ask for justification, so we can just say 7 to 10. All right, E, what is the change in position on 0 to 3? So change in position indicates displacement. So how much did the position change from 0 to 13, from t equals 0 to 13? Well, we find displacement by finding the integral. So the integral from 0 to 13 of v of t dt. So let's find the area. This is a trapezoid. Its base is 9, and this base is 1, 2, 3, 4, 5. Let's say 5. I'm calling this 3, an x value of 3 here, and 7. Oh, 3, 4, 5, 6, 7. Sorry. 3 to 7 would be 4. So our height goes up 1, 2, 3, 4, 5, 6. Height of 6. Okay, so let's find that trapezoidal area. So this first piece is 1/2 base 1 plus base 2 times the height. So 1/2, 13 times 6. 6 times 1/2 is 3, so this is 13 times 3, which is 36. All right, so this first piece is 36. Now let's see what the area is for this triangle. It goes 1, 2, 3, 4, so 4, and has a height of 3. So that area is 1/2 base times height. And it's below the x-axis, so it's going to be negative. So this ends up being -6. Okay, so we have a positive displacement of 36, then we go -6. So we've gone 6 in the other direction, which means our total displacement, when we add these together on this interval, ends up being 30. 30 meters, or whatever the units are for this problem, 30. Okay, the next question is, how far did the bug travel? Well, we can look at the displacement in each section and take the absolute value and add those together. So here, we had a distance of 36 for the first section. Let's see, that should be a 3, 36. And a distance of 6 for the next section. Now, it was originally -6 because that took into account the direction. But here we're just talking about total distance traveled no matter which direction you're going. So our first leg of the trip was 36, and the second was 6. So that gives us a total distance traveled of 42. All right, that is it. You hopefully read through the explanations on this last page, and hopefully if you needed some review on particle motion on various types of questions, you got some of that. We'll do more particle motion problems in class.